Welcome to the IUPI Reservoir Engineering Overview module in the Reservoir Appraisal and Development Planning phase of the E&P lifecycle. There are no prerequisites for this module. Upon completion of this module, you should be able to explain how to establish a viable project, identify when establishing viability is required in the life of a field, and on what sound principles a reservoir evaluation is based. Describe parameters used in estimating hydrocarbon reserves, and identify how they are used. Identify variables specifically associated with production rate forecasting, and how they are used in the basic radial flow equation. List various sources of data, and what information can be obtained from them, and how it can be used to determine field development viability. The role of the reservoir engineer is to evaluate available well and reservoir data and make the best predictions possible to help determine the recovery potential and commerciality of a field. The reservoir engineer may be called upon to join the technical team at various points in the life of a field. This individual can become involved before the first well is even drilled, during the exploration phase, to help evaluate the prospect. Or, the reservoir engineer can become involved after the field has been discovered and delineated, to determine the reserves in the field and plan its development. The reservoir engineer can also work on mature fields to maximize recovery from the field, looking for infill drilling or recompletion opportunities. Let's focus on the role of the reservoir engineer in a new field venture. Data obtained from wells during the exploration phase are analyzed in order to answer some key questions about the commerciality of the field. Not only does the reservoir engineer determine if the field should be developed, but this individual will provide input into how to best develop the field if the go-ahead is given from the oil company's management. For the most part, the decision to develop a field and how it is developed is based on sound, well-established engineering and economic principles. The reservoir engineer must analyze cash flow projections that are not only based on hydrocarbon recovery estimations for the field over time, but the price that the hydrocarbon will sell for in the market. The cash flow analysis must also take into account the upfront field development investment and the cost to operate the field. As you can see, there are many variables that must be considered, and while every attempt is made to quantify the analysis, reservoir engineering is a combination of art and science. There are several types of oil and gas reservoirs. These reservoirs are characterized based on geology, the type of hydrocarbon produced, and drive mechanism. The geology of the reservoir refers to the lithology of the formation and the manner in which the hydrocarbon is trapped in it. The majority of reservoirs consist of either sandstone or carbonate lithologies. A reservoir can produce gas, oil, or both. Water is also likely to be produced. A gas reservoir is one in which the predominant product is gas. This gas is called non-associated gas. An oil reservoir produces primarily oil. The gas that is produced from an oil reservoir is termed associated gas because it is associated with oil. As part of creating an overall development plan for a field, recoverable oil and/or gas reserves must be estimated in each reservoir. The data that are used in the estimation of reserves by using the volumetric method are the following: porosity, water saturation, net pay, area, pressure BGI, BOI, recovery factor. In this section, we will describe each parameter and provide information on how it is used to estimate reserves. Porosity is the fractional void space within the reservoir rock that is available for the storage of fluids. There are two basic porosity types: primary and secondary. Primary porosity refers to the fact that the porosity was formed at the time that the reservoir sediments were deposited. There are several types of primary porosity, including intergranular. This type of primary porosity is termed intergranular because it occupies the space between the individual grains that make up the rock. Sandstone reservoirs are an example of reservoirs with intergranular porosity. Intergranular porosity typically ranges from a few percent of the total rock volume to as high as 35 to 40%. Secondary porosity refers to the space in the formation rock which was created by geologic processes after the formation had been deposited. Vugular and fracture porosity are both examples of secondary porosity. Secondary porosity values can range from a few percent in the case of fracture porosity to as high as 50 to 60% in some very rare fields that are extremely vugular. We will present examples of how to calculate or estimate these values later in the course. The porosity, or void space in the reservoir rock, is initially filled with water. The water is later displaced by hydrocarbons, as previously covered in the exploration phase of this course. In order to determine reserves, the amount of oil and gas occupying this volume must be known. Initial saturation is the percentage of rock porosity that is occupied by water, oil, and/or gas at the time the reservoir is discovered. Connate water, or water saturation, refers to the water that exists in the reservoir when it is discovered. It is expressed by dividing the estimated water volume by the pore volume of the reservoir rock. Once water saturation is determined, then the balance, expressed as a percentage or a fraction, is the hydrocarbon saturation. Residual oil or gas saturation is the amount of hydrocarbon left behind in the reservoir when the corresponding oil or gas phase relative permeability is equal to 0. The figure represents typical oil-water relative permeability data. Usually, the experiment is done in the direction of increasing water saturation to simulate water injection in the reservoir. The base used to normalize the relative permeability data is the effective oil permeability at the irreducible water saturation. As the water saturation increases, the relative permeability increases until it reaches a maximum at the residual oil saturation. This term is important in determining the recovery factor, which we will be discussing shortly. Secondary or tertiary recovery projects, which we will learn about later, are put into place to reduce the hydrocarbon saturation over what can be achieved by primary recovery methods. Net pay is a measure of the thickness of the reservoir rock containing producible oil or gas. The net pay may be contained within a continuous interval, or may be distributed within a thicker package of pay and non-pay because of variations in rock properties or layering of sand and shales. Net pay is measured in true vertical depth, either feet or meters. You should be careful to note that there is a difference between true vertical depth and measured depth in wells that are deviated. In order to determine the reserves in a field, the areal extent of the hydrocarbon accumulation must be known. The areal extent of a new discovery is usually determined by a combination of seismic data, well testing, and delineation drilling. The knowledge of the structure and the water-oil or water-gas contact will define the area of the reservoir. Delineation drilling and well testing provides additional information to determine how far the reservoir extends and the location of fluid contacts. To minimize the cost of drilling delineation wells, the location of the wells should be carefully planned to obtain the most information with the fewest number of wells. Often a delineation well will be drilled and then sidetracked to gain additional information and minimize cost. The initial pressure in the reservoir is needed to determine the hydrocarbon in place. The pressure can also be used to determine if the reservoir is normally pressured, underpressured, or overpressured. A normally pressured reservoir will have a pressure that is consistent with the gradient of water at that depth. The initial pressure is also used to calculate the formation volume factor, or FVF, for each phase in the reservoir. The formation volume factor is used to adjust for fluid volume differences between the reservoir and the surface due to pressure and temperature. Because hydrocarbon volume is measured at standard conditions, the volume of oil or gas is different in the reservoir than at the surface. We've just learned a number of very important physical parameters that are used to characterize a reservoir. Let's see how these parameters are used to calculate the original hydrocarbon in place. Here, we see the equation for the original oil in place, or N. This is a similar equation for the original gas in place, or G. For each of these equations, you can see how the parameters that we've just covered are used to calculate the original hydrocarbon in place. The original hydrocarbon in place is exactly that, in place. But what can we expect to recover from the total hydrocarbon that has been calculated using the previous equations? The answer is by applying a recovery factor to the total in-place volume calculated. In other words, we don't expect to produce all of the hydrocarbon that is in the reservoir, but a percentage of it. This percentage is called the recovery factor. The recovery factor is a very subjective number and varies from reservoir to reservoir. Nonetheless, by knowing what type of reservoir depletion mechanism is in operation, we can get a pretty good idea of what recovery range we can expect from primary recovery efforts. There are 5 basic reservoir primary drive mechanisms for oil reservoirs: solution gas drive, gas cap drive, water drive, combination drive, and gravity drainage drive. And 2 for gas reservoirs: volumetric reservoir, or gas expansion drive, and water drive. Volumetric gas or oil reservoirs are driven by pressure depletion in the reservoir, which originates from the expansion of fluids in place. Production from volumetric gas reservoirs is said to be highly efficient due to the high recovery factors that result, often as high as 90%. Volumetric oil reservoir recovery factors can vary widely, depending upon reservoir fluid properties. Solution gas drive oil reservoirs are driven by the gas that comes out of solution as the pressure drops. Gas cap drive oil reservoirs produce by gas cap expansion. The expanding gas cap helps maintain pressure as the oil is produced. Recovery from gas cap drive oil reservoirs is often enhanced through gas reinjection programs. The drive mechanism for oil recovery in water drive reservoirs is from the pressure support provided by the aquifer. In addition to pressure support, oil recovery in a water drive reservoir can be enhanced by the sweeping effect that the water has on the oil when it moves from the aquifer through the producing reservoir. The recovery factor is the fraction of the original hydrocarbon in place that is recoverable from the reservoir. In gas reservoirs, the recovery factor is primarily a function of pressure depletion from the initial pressure at discovery to the pressure at abandonment. Abandonment pressure is usually based on economic considerations. In other words, when it becomes too expensive to produce the gas. Recovery factors for gas reservoirs can be as high as 90% of the original gas in place in pressure depletion gas reservoirs. Recovery factors in oil reservoirs vary based on the rock type, depletion mechanism, and the properties of the reservoir fluids. Values can range between 10% in some primary depletion reservoirs to over 30%. It is important to point out that these recovery factors are based on primary recovery. Secondary recovery and tertiary recovery techniques can increase recovery by displacing oil left in the reservoir. The economics of initiating secondary or tertiary recovery programs in a reservoir must be evaluated based on the incremental oil that will be produced. Once reserves are estimated, predicting the production schedule of those reserves over time needs to be performed. This prediction, or forecast, combined with the sales price of the hydrocarbon, will help to determine project economics. Several parameters, in addition to some from the previous section, go into estimating the production forecast for the field. In this section, we will discuss these and other parameters and their relationship to quantifying production, relative to the radial flow equation shown here. One of the more important factors used to determine flow rate is permeability. Permeability is a property of the porous medium, and is a measure of the capacity of the medium to transmit fluids. Under the same conditions, reservoir rock that has low permeability will not allow fluid to flow at as high a rate as reservoir rock that is characterized by a high permeability. Permeability is measured in darcies. Because most reservoirs have permeabilities under a darcy, the more commonly used measure is actually millidarcies. Flow rate is directly proportional to permeability. It is a property of the reservoir rock and is a function of such things as tortuosity, pore size and distribution, pore throat geometry, and the fluids present. Relative permeability is a parameter used to characterize the ability of a fluid to flow in the presence of other fluids. The presence of water in the formation can actually reduce the ability of hydrocarbon to flow in the rock. Relative permeability is defined as the ratio of the effective permeability to a fluid at a given saturation to a base permeability. The base permeability is commonly taken as the effective permeability to the fluid at 100% saturation. Laboratory tests are conducted on cores to determine relative permeability ratios, which are then applied to the permeability in calculations which are used to predict flow. Viscosity is another parameter that determines the flow potential for a well. Viscosity is a property of all fluids and is the resistance to flow exerted by a fluid. It is measured in the laboratory from fluid samples obtained from the reservoir. Viscosity is measured in centipoise units. A fluid with a low viscosity, like gas, flows more easily than a fluid with a high viscosity. Oil viscosities vary greatly from light crudes to heavy oils, which require special extraction techniques. The pressure drop, or delta pressure, refers to the differential pressure occurring between the wellbore and the reservoir. In field units, it is expressed in pounds per square inch. This pressure differential is the driving force behind fluid flow. The higher the differential, the higher the flow rate. Another important parameter that is used in calculating flow rate is the drainage area. Drainage area is defined as the area of a reservoir in which a single well serves as a point for the drainage of reservoir fluids. In this section on production rate forecasting, we have learned about a number of physical characteristics that are used in determining production rate. Presented here is the radial flow equation for oil, and this is the radial flow equation for gas. You can see from the equations how the parameters are used in calculating flow rate. This equation, the radial flow equation, is one of the key equations used in the estimation of flow into a wellbore. There are many sources of data available to the reservoir engineer. This data can be collected before, during, and after the drilling of a well. In this section, we will examine some of the more common sources of these data. It is important to point out that the request for relevant data during field development is often the responsibility of the reservoir engineer. Careful planning and teamwork before a project begins can yield big dividends. The quickest and most inexpensive way to gather information about a reservoir or well is through published databases. These databases are available through government sources or commercial ventures that sell the data. The use of offset well data can provide the reservoir engineer with a wealth of information about the well that is to be drilled and completed. In addition, the use of regional or offset well data can go a long way in filling in the blanks for any specific well. Many fluid parameters and reservoir properties can be quite similar over regional areas. Mud logs are generated during the drilling process. Mud loggers collect samples of rock cuttings that are circulated to the surface by the drilling mud. The cuttings yield information about the reservoir lithology. The examination by the mud logger can also provide indications of hydrocarbon and porosity. The mud is monitored for shows of gas that may have been liberated from the formation as it is being drilled. Any significant inflow of fluid into the well will show up as an increase in the mud volume or a decrease in the weight of the mud. Once a well is drilled, special tools to investigate the formation are run into the well on wireline. These tools are called logging tools. They produce electric logs. Logging tools provide a great deal of information about the well and the reservoir, such as lithology, porosity, and water saturation. When logging tools are run into the well before a casing is run, they are called open-hole logs. We discussed how formation cuttings are used to provide information which form the basis of mud logs. Larger samples of downhole rock can be obtained by coring a well. A special bit is used to cut rock while the formation is being drilled. This resulting rock sample is called a core. The core, usually cut in a 30 to 60 foot section, is brought to the surface and carefully packaged for transportation to a laboratory. At the lab, measurements of such properties as porosity, permeability, and other parameters are made. Coring is a comparatively expensive operation. In a new field, for example, only a few wells might be cored due to the high cost. Drill stem tests, or DSTs, are done while the well is being drilled. Special assemblies are made up in the drill string and allow information about the reservoir pressure and fluid to be obtained. This test is carried out by allowing the formation to flow into the modified drill string. Pressure and fluid data recovered during the test can be analyzed to determine the potential productivity of a formation or individual zone. DSTs are not always conclusive, given the limited time that the flow period occurs. A method of testing the formation that yields similar data to the DST is called downhole formation testing. This technique uses a tool-conveyed wireline to investigate the zone of interest. Downhole formation testing tools, such as the repeat formation tester or the modular formation tester, mechanically extend a probe to seal with the formation. Once sealed, pressure and fluid samples are recorded and taken for analysis. Once casing has been run in the well, a zone can be tested by perforating across that zone. Perforating allows fluids in the reservoir to communicate with the inside of the cased hole. After the zone is perforated, the well can be tested by allowing formation fluids to flow up the tubing to the surface. Flow rates, fluid composition, and overall productivity can be assessed. Samples of produced fluids can be taken and sent to a lab for analysis. Pressure buildup testing can be conducted immediately after flow is suspended from the test. In a pressure buildup test, a flowing well is shut in, and the pressure recorded either at the surface, downhole, or both. Downhole pressure measurement is the most common method and generally provides accurate data. The pressure buildup test can provide information such as the average reservoir pressure, permeability, and many other reservoir parameters. Now that you've completed this module, you should be able to explain how to establish a viable project, identify when establishing viability is required in the life of a field, and on what sound principles a reservoir evaluation is based. Describe parameters used in estimating hydrocarbon reserves, and identify how they are used. Identify variables specifically associated with production rate forecasting, and how they are used in the basic radial flow equation. List various sources of data, and what information can be obtained from them, and how it can be used to determine field development viability. First, we reviewed the basics of reservoir engineering, including the role of the reservoir engineer and the types of reservoirs. Then we considered the parameters that must be examined to determine recoverable hydrocarbons in reservoirs. These parameters include porosity, water saturation, net pay, area, pressure, depletion mechanism, and the recovery factor. To determine the economic viability of a field, a production rate and forecast must be made based on permeability, viscosity, pressure drop, and drainage area. The radial flow equation can then be used to make estimates. The sources of data available to the reservoir engineer could include regional data, mud logs, electric logs, cores, DST, and production. The engineer will carefully consider all the available data before planning the development of a reservoir, as we will see in the following modules.